So today we're going to start chapter number 5, and we always start the chapter with a guide post. In the early chapters of this book, you looked at the sky the way ancient astronomers did, with the unaided eye. In this chapter, you will see how modern astronomers use telescopes and other instruments to gather and focus light and its related forms of radiation. That will lead you to answer 5 essential questions about the work of astronomers. What is light? How do telescopes work and how they are limited? How do astronomers record and analyze light? Why must some telescopes go into space? Astronomy is almost entirely an observational science, so astronomers must think carefully about the limitations of their instrument. That will introduce you to an important questions about scientific data. How do we know? What limits the detail you can see in an image? And the outline, the first part will be radiation and how we get information from space. Then we will talk about optical telescopes. And then we'll talk about astronomy from space. So we're going to look at the first part here, which basically radiation from space. And there is a common misconception here at the start. And that's when you hear the word radiation and people are always alarmed. We have what we call non-ionizing radiations and ionizing radiations. Okay. So anything that radiates, basically it radiates energy. So even yourself, as you are sitting, you're basically radiating infrared radiation. And we'll talk about all these different types of radiation. So light is a form of radiation. And light is basically what humans have been using to look at things. Is when it comes to astronomy, they look at the planets and stars in the night sky. So in astronomy, we really cannot perform experiments like, for example, what you do in biology. You can take a frog, you dissect the frog, you can basically look at different aspects of leaves, whatever it is. In chemistry, you can start mixing solutions and things like that. So usually here you can experiment with things. But when it comes to astronomy, I cannot bring the moon here or go very easily to the moon or bring the sun, or that's not something feasible. So astronomy relies on observation. And that's why we say astronomy is an observational science. So you only have to observe. And you do that from here on the surface of the Earth. So the only way we can analyze or understand what we are looking at, we have to rely on what we get from these objects that we see in the sky. What do we receive from them? And what we receive from them is basically radiation. And light is a form of radiation as well. And light has a very interesting story. Okay. Now we'll deal with light as a wave, but let me just briefly try to go probably through some points through history of how we got to understand light. Light is essential. We see things because of light. The Greeks, they brought in a philosophical question of what is light? Is light a form of matter? Is it energy? What is it? And finally, they came up with a concept that we see things because the eye shines light on the, and then you see these objects. And as I told you in the previous lectures, that the Muslim civilization started with an era, or the era of translation. So they tried to collect the works of a previous civilization, and they translated it to Arabic, and they wanted to make sense of it, and they were critical of things that are not right. Now, Al-Hasan ibn al-Haytham, and many regard as Al-Hasan ibn al-Haytham as the father of optics. And as I told you, sometimes in Western civilization or European writings, they may refer to him as Al-Hasan, not Al-Hasan. And there is a big difference between the two. Al-Hasan ibn al-Haytham is very smart. During the time of the Al-Khilafa al-Fatimiyya, the Fatimi Khilafa in Egypt, he heard of the problems that are encountered with the Nile, floodings and so on. And he said, well, I can use this to the benefits of the Khilafah. The Khalifa, of course, heard of that. They invited Al-Hasan ibn al-Haytham to Cairo, and he was well received. And then the time came to implement his ideas. So he went on a tour to the Nile, and when he saw the Nile, he realized that he cannot do what he thought he was able to do. Of course, he came back to the castle, and he cannot tell the Khalifa that I cannot do this. So after careful thinking, he decided to play mad. Okay. So they said, Junna ibn al-Haytham. Khalifa said, I don't care. He's crazy, not crazy. Throw him in jail. No one plays games with me. While he was in jail, and you could imagine those whole days, he had lots of time, no form of entertainment and so on, but he's a man of science. So he started looking at light. He was pondering, I am in the cell, and when it's dark, I don't really see anything. I only see things when some light breaks into the cell. And from there, he started to set the idea of the Greeks that the eye shines light on objects, and then you can see them. That's very wrong. You only see things when there is light. So he said, we see things because light reflects off these objects. And that was a big correction. And of course, later on, the son of the Khalifa came in, and he released Al-Hasan ibn al-Haytham. Al-Hasan ibn al-Haytham basically started working on optics. He dissected the eye and understood how the eye basically saw it by the light that is reflected off the object to the eye, and the eye that basically does not shine light on object to see them. And he even created something which called al-qumra. And if we look at Al-Qumra basically, okay, if you take a box and you make a pinhole in the box and you look at an object, you basically going to get an image, but the image will be upside down. Okay. So we created that. Okay. And of course, from Al-Qumra, now we know it as camera. And things were known about light, which basically it reflects. So if you stand in front of a river or something like that, you see your own reflection. If you put something in a glass of water, it looks broken, but if you take it out, it's not broken, and that's known as refraction of light. But there are still questions. What is the light? Is it a form of matter? Is it a form of energy? Even the speed of light was not known. And people have attempted to measure the speed of light. You know, when you deal with the sound, so if you deal with sound, if you stand far away from a mountain and then you shout, the sound will hit the mountain and then come back to you, and that's an echo. So if you know the distance, if you have, let's say, a mountain here and you shout, if you know this distance that the sound will go through, and when it comes back to you, so actually if you want to get the speed, it will be twice this distance divided by the time from when you produce the sound to the time that you hear the echo. So Galileo Galilei tried to do the same thing with light. He actually brought a candle and he made a helper to go far away from him and a mountain, and he gave him also a lantern, and he told them, well, what I will do is I will uncover the my light source, and when you receive the light, you do the same thing. And he's waiting to receive the light from his helper, and he wanted to use the same concept. Now, just to give you an idea, the speed of sound, it's about 340 meters per second. That's about 1,000 something kilometers per hour. But the speed of light, as we discussed, that number one, it's 300,000 kilometers per second. It's very fast. So he was not able to measure any time, and he was trying to increase the distances and so on. So he came to the conclusion that he said it is impossible to measure the speed of light, or the speed of light is infinite. Later on, the speed of light was measured by different scientists in France and in England, and it came to be very close to the 300 kilometers per second. That's the speed of light in air or in vacuum. And when you go outside the atmosphere of the Earth, you don't have any air, so you're on vacuum. Okay? And that's how we receive the light that comes from stars and so on. So the speed of light was known, but it still, is this light a form of, is it matter or is it energy? And of course, you have two things to explain. It's basically the reflection of light and the refraction of light. Newton's, a very smart scientist, worked in many things. He assumed that light is made of very tiny particles, and when these particles basically hit a reflecting surface, they reflect. You can think of a tennis ball, you hit it at an angle theta to a surface, and it will be reflected back. It will be reflected off the surface at the same angle, and that's why in schools they tell you the angle of incident is equal the angle of reflection, and these are what's known about reflection of light. And when it comes to refraction, he said, well, you have two different media. One medium is the air, the second medium is, let's say, glass or water. And of course, when these particles will go through them, there is a difference in density between these two different media. And that's why for the particle to move, it's basically has to refract. Huygens, a Dutch physicist, he made a mathematical model, and he said, well, I can actually explain reflection and refraction of light if they travel like waves. So now he's thinking of light as energy. And it's still not known, but now one thing known, basically now the speed of light is known. In 1801, Young performed an experiment which we call the double slit experiment. In that experiment, there's something in light that we call diffraction of light, and he showed that light is behaving like waves. So when that was, that's a smoking gun. That's it. That's an evidence. So light is basically a form of energy. It is a wave. So it travels like waves. It has a very high speed. But there was a lingering question at that time. Now we know that if you want to experiment with waves, there has to be a medium to carry the wave. And the question was that if you do that in vacuum, like light is traveling through vacuum, so what is the medium that carries this? And that basically came with a wrong invention, which is the ether. And they said that there is a medium that exists even in vacuum, which is ether, and that's what's carrying the light waves or waves of light. Okay, so this is basically the idea of light when it was discovered to be a light waves. So now we know that light, it travels like a wave. It has a speed of 300,000 kilometers per second. And we have experiment that can basically show you that it goes like a wave. Maxwell was working on electromagnetic waves. And he derived equations where he actually showed that electromagnetic waves, they travel at the speed of light. It was done independently, and then light is basically regarded as an electromagnetic wave. And it has a very high speed. So a lot is known about light. And when light was considered, it looked upon as a wave. Till early 20th century, it was discovered that when they were looking at what carries electricity, electrons, and so on, so to make that short, you take a tube and you make a cathode and an anode, and you basically make this in a vacuum, and you try to heat to get electron, and then you can measure a current or a voltage. And this basically how it was the discovery of electrons. The strange thing is basically when light hits, it causes an electrical current. And that was known as photo. Photo means color, so they called that the photoelectric effect. It was not known why it does this. Einstein, he argued that light is made from very small particles called photons. And these photons, when they interact with the electrons, they knock them out of their orbit and they become free, and now they conduct electricity. And now, well, light is maybe matter. It's made now of particles called photons. But when they travel like waves. And that's now known as the dual nature of light. And that it's also for electrons. When they travel like waves, but they are made of particles and so on. And this is actually where it goes to duality in quantum mechanics, something that we call quantum mechanics. So science progressed and explained what light is. So a light is traveling at a very high speed. It's an electromagnetic wave. It's actually made from very small particles. We call them photons. Now, if anyone argues about matter or wave, the experiment that done by Thomas Young, a double slit, and that shows you the diffraction of light, and it is a wave. And if you argue that it's a matter, then you basically use the photoelectric effect, where you can show that light is composed of photons. And that's what Einstein basically got the Nobel Prize for. Einstein basically known for the theory of relativity, but he actually got the Nobel Prize for the photoelectric effect, for that explanation. So now, how do we look at waves? Okay. So before I start, I will give you here what it looks like a wave. And we will basically take between two crusts here. And the distance between these two crusts, we define them as wavelength. And it will repeat itself. Usually we use the symbol lambda for this, for the wavelength. And it will repeat itself in a time where we call it the period t. And the speed of light is constant within the same medium. Let's say if it's in air, it's going to be the same. If it is in vacuum, it will be the same. If it's through water, it will be different. It's not going to be 3. So the speed of light in air on vacuum is 300,000 kilometers per second, or it's 3 times 10 to the 8, because every kilometer contains 1,000 meters. 3 times 10 to the 8 meters per second. Now in water or glass, it may be 2.5 times 10 to the 8 meters per second, but it is different. So now, you know that if you want to calculate the speed, A speed always equals the distance divided by time. So if we do that with light waves, so the distance lambda, that's the one wavelength, and it's done in a period t, so it is lambda over t here, and that will give you the speed of light, which we know. Now, so it is hard to measure a period for one wavelength, but we can basically, as you can see in the figure here, instead of measuring the period for one wavelength, well, you can fix a period of 1 second, and then you count how many wavelengths that you get in 1 second. So you take the 1 second and you divide that by the period of 1, that will give you the frequency. So if we know the number of wavelengths that pass us in 1 second, and how that means how many frequent we see this in 1 second, and that's now known as the frequency, and it's given the unit hertz, honoring Hertz, who was working on this. So now we can take the 1 over t as frequency, and we can write the speed of light equals to the frequency multiplied by the wavelength. But this speed of light is not going to change. It's going to stay the same. So what's going to change? The frequency and the wavelength. So here, this is our relation. Speed of light is equal to frequency multiplied by wavelength. Wavelength is equal to frequency divided, wavelength is equal to speed of light divided by frequency, or frequency equals the speed of light divided by the wavelength lambda. And that's basically how you characterize the wave or light. You characterize in terms of wavelength and frequency. Of course, they related with the speed of light. So now, what units do we use in measuring this wavelength? The wavelength of light is very small. So we use units of nanometers. So if you talk about 1 millimeter, you're basically talking about 1 meter, and you divide that by 1,000. If you're talking about 1 micrometer, you take 1 meter and you divide that by 1,000,000. 1 nanometer, you're basically talking taking 1 meter and you divide that by 1,000,000,000. So it's a very small unit. Now we can write this, the 1 nanometer, as 10 raised to the power minus 9 meter. And that's what we have here. So we use a unit of nanometers. So the wavelengths, you know that you can separate light, which we call the rainbow colors. They go all the way from violet to red. And the difference between these colors, that they all have the same speed of light, but they will differ in the wavelength. And they have a range that goes from 400 to 700 nanometers. Now, there is another unit that is used, and the unit is to honor angstrom. It's given A with a subscript here, a small circle, and it's smaller than the nanometer. That means 1 nanometer contains 10 angstrom, or we can say that 1 angstrom is 0.1 nanometers, which is basically 10 raised to the power minus 10 meters, which If now we apply this to visible light, the range will be from 4,000 angstrom to 7,000 angstrom. So these are used, but nowadays mostly we use the nanometers. So the waves are very small. Just to give you an idea, the coronavirus, I think it's below 100 nanometers. And that's not, it's not, we cannot see that with our eyes, or we cannot see it with optical microscopes. We need electron microscopes to see that. So when it comes to light, and you can see here the cake that it's made of these different colors. We go from violet, then blue, green, yellow, orange, red. These are the rainbow colors, and the range, of course, will go from 400 nanometers to 700 nanometers. By the way, you have shades of every color, and these shades basically they're just differing in the wavelength as well. So you may have different shades of blue or different shades of orange. These are they will differ in the wavelength, and that's how we look at light as a wave traveling with a very high speed. So that's one thing known about light. The second thing that I told you about that actually, and that's Einstein basically got the Nobel Prize for this, which is the photoelectric effect, where light is made from small particles called photons. And you know, when things are traveling, they have energy. Probably you heard of the term kinetic energy and so on. So these actually particles are having energy, and that energy is given as HF. F here is the frequency of the light, and H is known as Planck's constant. And we're not going to go, he basically, he started the idea of quantizing what we call Bragg radiation and so on, and then later on, that's what led to quantum mechanics. So we use this Planck constant, and that will give us the energy of these photons. And that's why I told you Einstein explained them in terms that they will hit an electron, and if the energy is sufficient enough, they knock an electron out, and the electron basically can go around, leaves the atom, and with this basically you get what you get, your electrical current, which caused by this photoelectric effect. And by the way, this is how we get what we call solar cells. The scientific name for it is called photovoltaic cells. You're actually, it's materials where we use solar because we look at the light that comes from the sun, which is renewable. It's always coming, and it can hit these solar panels. It will eject electrons, and these electrons basically can conduct electricity. So we use this electricity. Of course, we have to save it, and that's why you may hear a lot now about advances in batteries and something called supercapacitors and so on. That's very essential for the energy that we need. So that's the energy that we get. We get the solar energy is basically coming from the light waves that basically hit the solar panel or the photovoltaic panels, and it works on the principle of the photoelectric effect. And we call it renewable because it's continually coming from the sun. So now, when we look at light, and that's what was available, that's what we call visible light. And for a very long time, humanity relied on looking at things with light. Okay, and by the way, many people, they say, why do we see different colors? We're not going to go into that, but the basic idea is when light strikes an object, it will absorb all these different energies or wavelengths, and it reflects only the part that you see. And I told you, you can, everything that you see, it has a certain frequency and wavelength, and you all know now, if you look, probably they don't do that anymore, but in TV, when it was a cathode ray, you can see 3 primary colors, which is red, green, and blue, and you mix these primary colors to get any color. So visible light was what was used to see things. But through the study of electromagnetism and electromagnetic waves, and then many forms of electromagnetic waves were discovered. And I think you all know the story about Röntgen with the X-rays. And now every hospital that you visit, they have X-rays, and they use these basically to see the status of your bones and so on. So we have a host of electromagnetic waves. All of these electromagnetic waves, they travel at the speed of light, and they're composed of tiny particles, photons, but when they travel like waves. And the only difference is when we talk about that the speed of light is equal to frequency multiplied by the wave length. So that's the difference. This is going to stay constant, but what will vary is the wavelength and the frequency. So now when we talk about the electromagnetic, and sometimes we use a symbol EM, and E stands for electricity, M magnetism, so we saw EM here, and we call it a spectrum, and a spectrum is a collection of things. That's why we call it EM spectrum or electromagnetic spectrum. And there are many radiation that are regarded as electromagnetic waves. There is the gamma rays, the X-rays, the ultraviolet. You look here at visible light, and visible light is only a small portion of this. It's not a very big portion. And then infrared, and you yourself actually emitting infrared radiation. And that's why you can be seen in the dark if we use a filter that can detect the infrared. And then you have microwaves, and you know that in every kitchen you have a microwave, and your communication with mobiles is done with microwaves. And then you have the UHF and the VHF, and that's basically the ultra high frequency and the very high frequency. And these are used by for TV and so on, that are radio waves. And then you have the FM and the AM, which you get in your radio and so on. And that's why we call it a radio, because it relies on electromagnetic waves, but in a range where we call this radio waves. And they're not sound waves. Sometimes people they listen to a radio and they hear radio waves are electromagnetic waves. And this electricity is used in something called transducers and so on to convert it into sound. So this electromagnetic waves, they travel with the speed of light, but the only difference is going to be in the frequency and the wave length. So as you can see here, we're expanding this small portion here, and this is where we have the visible region, which goes from 400 to 700 nanometers. So if you go this way, the wavelength is going to increase. And if you go this way, the frequency is going to increase. So you can see the wavelength here, they can go as 10 raised to the 2, which is about 100 meters, or 10 raised to the power 4, which is about 10,000 meters. And that's why sometimes if you're listening to radios and so on, because there are things comparable to the size of this wavelength and they kind of block them and diffract them and things like that, and that's why you're not able to get them. Okay, so that's basically what we call the electromagnetic spectrum. Now we produce this radiation here on Earth, but the sun, for example, it's producing all these electromagnetic radiation. And of course, they radiate from the sun in all directions. They go through the whole solar system. And they come to us here on Earth. But on Earth, we have something special, which is the atmosphere of the Earth. And this atmosphere of the Earth blocks the gamma rays, the X-rays, the ultraviolet, and it allows the visible light to reach the surface of the Earth. When it comes to infrared, reaching the surface of the Earth, as I told you, you are producing infrared, but we're interested in the infrared that comes from the sun or outer space. So we want it to go through the atmosphere of the Earth. We can go a little bit high in the atmosphere to detect that, but it's also blocked. And then the radio waves can penetrate and come through. So when we want to study the radiation that comes from the sun, for example, and we want to do it here on the surface of the Earth, then there are two forms of radiation that we can use in observational astronomy here. It's either visible light or radio waves. Other forms of radiation which we produce and we can study here on the surface of the Earth, but the ones that come from the sun, we have to go above the atmosphere of the Earth to study this. And that's why if we want to make any instrument that can detect the gamma rays, the X-rays, things that come from the sun, we have to do that from space. We cannot do it from the surface of the Earth here. So that's why now we came a long way from just relying on our eyesight to using now radio telescope and optical telescope, and then putting things in orbiting the Earth to look at this radiation that come from space. In this slide here, it's the same slide, it just looking at the different electromagnetic waves. So if you look at them, it's gamma rays, X-rays, X-rays sometimes known as soft and here and hard. You don't have to worry about this. Ultraviolet, visible light, infrared, and radio waves. And you can see as you go this way, the frequency increases. And the frequency, it means how many wavelengths in 1 second. So you can see for gamma rays is 10 to the 23. And the wavelength is very small. That's why they can penetrate your tissues. And X-rays, for example, can give details of your bones and so on. Now, this is just to give you an idea of these sizes. Okay. So, for example, radio waves of the order of 10 to the 4, which is 10,000 meters, could be like the Mount Everest, a skyscraper for 101 meter. We're talking about human. When we talk about millimeters, then you're talking about human finger. Then micron size, you're talking about dust. Then less than that, you're basically, in terms of micron, you're talking about bacteria. Less than that, then you're talking about in nano range, you're talking about viruses, and you can go all the way to talk about an atomic nucleus. So in astronomy now, we know that the sun is sending all of these radiation, and by observing this radiation, we can understand a lot about the sun, but the instrument and the tools that we need to observe this. So I spend some time here to tell you about electromagnetic radiation. I just wanted to make clear what we mean by electromagnetic waves. And I want you to know that light is basically known as electromagnetic wave. And it only has a small range in this electromagnetic spectrum. Now, sometimes you may actually hear scientists and astronomers, they talk about light where they're actually doing things in radio wave, or they're doing things in X-rays and things like that, because they just refer to some, okay, they refer to them as light. But light to us is known as visible light. So usually we say visible light. Okay, we have to indicate that. And as I told you, I think when I was going through this, I don't want you to confuse radio waves with sound. And radios, we actually listen to it. It's producing sound, but actually it relies on radio waves, which are electromagnetic waves. TV, for example, we can see things and hear things. It uses radio waves. But of course, you have things that can convert because you produce them and you send these waves. So I don't want you to confuse radio waves as being sound waves. Sound waves are different. Sound waves is basically, they need a medium to travel through. They need air. They need something that they can travel through. Electromagnetic waves, they can travel through vacuum. So there is an experiment where you take a jar and you put an alarm clock with two belts where you can basically look at it, and you have an opening. It's open here. When the time comes, you see the alarm moving and you hear the sound. But if you evacuate all this air out and you set it at a certain time, and when you see the alarm moving, you actually cannot hear the sound because it's evacuated. So sound doesn't travel through air. But if you do that with, instead of using the alarm, you put a light alarm, it will work either if there is air or no air. That means light will travel through vacuum, but sound doesn't. So sound is different. And I told you about the speed of sound. It's about 340 meters per second in air, but light is 300,000 kilometers per second. So there is a difference between these. So you have to be alert of this. So most waves require a material medium in which to be transmitted. Okay. That's when we talk about water waves, sound waves, if you need an earthquake as well. But EM, which electromagnetic waves, may propagate through pure vacuum at the speed of light. And that's when you leave the atmosphere of the Earth here. Light basically, or electromagnetic waves, can come from the sun and stars from space. So I'll try to summarize this first part here. Light is a form of electromagnetic waves. And of course, we talked about the speed of light, and we said it's equal to 3 × 10⁸ meters per second. And we said this speed of light is equal to frequency multiplied by wavelength. And we said light travels like waves, but also made of tiny particles. We call them photon, and the energy of these photon is equal to hf, where h is Planck's constant. And that's what we call the dual nature of light. Now, the complete electromagnetic spectrum include gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. And the Earth's atmosphere is transparent only to two forms of electromagnetic waves: visible light and radio waves. And that's basically what reaches the surface of the Earth here. So if we want to do observation, and that's what basically when Galileo Galilei became aware of the telescope, and he made his first telescope. So he was using to look at visible light. Now we use also radio waves, and we'll explain this as we move on, but other radiation have to be done from space. Now, just to give you an idea on how important this atmosphere that we have around the Earth, I usually tell people, if you are the Earth, then the hair on your head is the atmosphere. So it's really that very thick protective layer. Okay. And if you regard it as an apple, it's basically the skin that you have in the apple. So we have to be careful with our atmosphere. It's protecting us from harmful radiations and so on, which probably can harm life here on Earth. So we have to be careful with our atmosphere. So an astronomy is an observational science, and we really have to rely on these forms of electromagnetic radiation. And I told you there are some that we can do here from the surface of the Earth, and there are the ones that we really have to go to do that from outer space. So I think I'll stop here, and I want to see if you have any questions. Do you have any questions on these? You can use the mic as well if you like. You can turn the mic on and you ask the question, but please turn it back once you're done. Oh, good. It seems clear. So good.